we're very happy to have Max Guillen from ICTP in Sao Paulo visiting us here. He's going to tell us about the Supertwistor descriptions of the Ambitwistor strand. That's right. All right.
Thank you. Thank you so much for the invitation. It's really a pleasure for me to be here and give this talk for you. So please feel free to interrupt me if you have any questions or comments, okay? Okay, so I'm going to start with the motivation of the talk. So let me write that title. So it's the description of Ambitwistor strings. Okay. So the motivation is very simple. So it's well known that Supertwistor techniques in D+4 have been shown to be very powerful and useful for describing N=4, D=4 super-Young resamples, right? So since this model, N=4, D=4 super-Young can be obtained from compactification of the N=1, D=10 super-Young mills, it's natural to ask if the existence of some Supertwistor framework in D=10 can be proposed or constructed in such a way that 10-dimensional amplitudes can be described in a powerful way or in an elegant way, right? In this sense, I'm gonna introduce the 10-dimensional Supertwistor description of the superparticle, okay? And then we will see that this Supertwistor description can use it in order to formulate an Ambitwistor string, okay? So in order to do that, let me start with a very well-known model, which is the D=10 Quantization superparticle, massless, okay? Okay, so the action is given by the word line expression in the first order plus the constraint, right? Because I'm going to work on the matrix case, okay? So it turns out that this action is invariant under the global super Poincare group and also under supersymmetry. So the supersymmetric transformations can be read in this way. And it turns out that this action is also invariant under the so-called kappa symmetry, which is a local fermionic symmetry. Okay, and the transformations can read as follows: where kappa is an anti-vibe, if you want, SO1,9 spinor, SO1,9 spinor, sorry, minor and vibe. Okay, and here. Xm varies like this. En doesn't vary, and E varies this way. Okay? And of course, this action is also invariant under the diffeomorphism symmetry, right? Okay. So it turns out that one can use these two gauge symmetries in order to reduce the phase space. So for example, I have 20 degrees of freedom in X and P, right? And I have 16 degrees of freedom in theta, right? So if I use these two gauge symmetries, which is kappa symmetry and diffeomorphism, I can reduce this space to the Witten superambitwistor space, which has this dimension, a thing and n. This is bosonic and this is fermionic, okay? So now I'm going to introduce a Supertwistor transform, okay, with some constraints. And it turns out that in this new Supertwistor approach, we will see that these twistor variables, after imposing these constraints, I will reproduce the same degrees of freedom as the 10-dimensional Green-Schwarz massless superparticle. Okay? So now, let me introduce the Supertwistor transform. The 10-dimensional massless superparticle. Okay, so I'm gonna denote it by DCA, and I will use these two Majorana spinor of opposite chiralities, and a fermionic vector here. So lambda alpha is SO1,9 Majorana by spinor is real. Okay. W alpha is also SO1,9 Majorana spinor. Let me put here, I don't know, chiral and antichiral, and also psi m is SO1,9 vector, fermionic vector. Okay. Okay. So here I have 16 degrees of freedom, and here I have 16 degrees of freedom, and here I have 10 fermionic degrees of freedom. Right. So the idea is that I have to obtain the same degrees of freedom that I obtained here. Okay? So in order to do that, I will impose some constraints. Let me write these constraints. The first one is given by this expression. And the other one is given by this expression. Okay? You can count here, for example, 16 degrees of freedom, right? And here 1 fermionic degree of freedom, or 1 gauge symmetry. I mean, 1 constraint which will generate a gauge symmetry, right? So let me put here 1 fermion and 1 boson. So 16 bosons. Okay.
At the moment, lambda is just a complete unconstrained spinor. Right?
That's right. This is
It's
a
not
pure
spinor.
Yeah, this is an ordinary spinor of SO1,9. Okay. So now it turns out that these constraints are not independent of each other. Actually, you can show that lambda gamma g minus 2 psi m df is equal to 0.
What is G?
G is this one. I mean, this is lambda. So sorry. So gamma, m, alpha, beta are the Pauli matrices of SO1,9. So, okay, SO1,9 has 32 times 32 components. So gamma AB, but this can be written in this way: gamma m alpha beta, gamma m alpha beta. So these gammas are these gammas here, and these gammas are the same gammas here.
I think the problem is that the G looks like a C.
Oh, so I'm sorry about that.
No, on top. On the top.
Here?
Yeah.
Oh, sorry. Okay, thank you. Fine. Okay, but it turns out that if we use the standard 10-dimensional Friis identity, which is this one, sorry, gamma m alpha beta, gamma m delta sigma, symmetries in 3 indices, this is 0, right? So it turns out that the coefficients here are also constrained. Okay, so we have here a system with constraints, which is a reducible system. Okay, so yeah, sorry.
Why is psi m constrained at this point?
Why psi?
Yeah, psi, right, at this point is arbitrary vector, right?
Yeah, because if I use this, I mean, lambda gamma lambda times these coefficients, this is again TF.
Oh, I'm sorry, yeah. Okay.
Okay, and when that's a good point. So lambda gamma and lambda times this coefficient is 0, identical, because of this idea. So now I have to use, there is a well-known procedure to study this kind of systems. This is shown, for example, in the Hinox book, which is called Quantization of Gauge Systems. Okay. So it turns out that we have to take into account these reducible gauge symmetries by introducing goals for goals for goals. Okay. Okay, it turns out that this system has a level 2 reducibility. This means that, for example, I will start with these goals for G alpha and TF. Let me put okay, B alpha, C alpha for G alpha. Then I have these goals beta gamma for TF. Okay. And then I will have to introduce goals for this. Let me put here HN, for example. Okay. So I will have to introduce these goals, beta m, gamma m. And finally, I have to introduce scalar goals here because of this. of these conditions. So I will have ET CQ. So first generation, second generation, and third generation. Okay?
So this is a nice question, just to remind me. The fact that there's a relation between those three constraints is implying that there's the third level of ghosts? Or,
Sorry, could you repeat?
oh, sorry, so you have three different constraints, right?
Yeah.
G alpha and TF, but they're related.
Yeah, that's right.
So I'm just trying to understand, I'm just trying to remind myself, what does that imply for the ghost sector?
So you have to add ghosts for each reducibility constraint. For example, I have this reducibility condition, so I have to introduce these ghosts.
Right.
I have this reducibility condition, so I have to introduce these ghosts. That's the relationship between the gauge symmetries of the constraints and the introduction of ghosts for ghosts in your model.
Right, so then the B alphas were just from the G alpha?
Yes.
Okay.
That's right.
And then just to make sure I understand the global picture, at the end of the day, are you going to end up with a translation table between the twistor variables and the original Frank-Schwarz variables?
Yeah,
Or are they going to
yeah.
end up at the same place?
Yeah, at the end of the day, I want to use these variables in order to rewrite this model in terms of these supertwistor variables. Okay?
You put a box around the Field's identity. Did you mean to do that? Is there really a ghost for the Field's identity?
Yeah, I mean.
Which one is it? I mean, you wrote it to the scalars, but of course that's not possible because it's a spinorial one.
No. The point is that this alpha.
Oh,
is
just
the-
one
is
more
the
lambda.
index. Yeah. Okay. So now, in order to solve these constraints, I'm going to write the relationship between the superspace coordinates and the twistor variables. Okay. So it turns out that the solution for these constraints is given by this expression, which are called the incidence equations, right? This way. Okay. And since I studied the massless case, I'm going to write Pn in this way. Notice that lambda is a constraint spinor, okay? There is another model introduced by Berkowitz also in 2009, I think, yeah, 2009, yeah, where he used, well, this is just as a comment, he used a pure spinor and unconstrained spinor here. He tried this because he tried to relate this formalism with a pure spinor formalism of string theory. But there are some issues there which are not so clear so far. So okay, this is just a comment.
Wait, could you say that again? Because I think I'm actually more familiar with the second one. Which one is that again? Can you tell me?
This is
This is
given
the
by
one?
Berkowitz in 2009. There is the title of the paper is like 10-dimensional supertwistors and the equation superior means.
Okay.
Yeah. So this is a
In
pure
that
spinor,
one on the right, that's a pure. Okay.
and this is not a pure spinor. Okay. But there are some problems with this model. We can try to talk later if you're interested in that.
I'm a little bit confused about what the incidence relations are telling me. Because I'm
This
just trying to,
one's-
I'm trying to come, what degrees of freedom. Like, are they translating me from the Supertwistor description to the Frank-Schwarz description, or vice versa?
That's right. Yeah.
Okay.
There's this is the map between the Schwarz formalism with the supertwistor formalism. And this map is the solution of these constraints.
Right, but I mean, the number, I'm just trying to think.
Ah, yeah, okay.
Oh, you're saying both of them are 18, comma 8, so that's
Yeah.
why it's invertible.
Yeah.
Okay.
And now I can try to count here the degrees of freedom, for example. So I have here 16 constraints, right? But here I have a constraint of the constraint, which is null, right? I mean, sorry, it's not null, but lambda gamma and lambda HM is 0. So actually, I don't have 10 constraints. Instead of that, I have 9 constraints.
Right.
So I have 16 minus 9 independent constraints, right?
Okay.
Bosonic. And I have 1 fermionic constraint. Okay, so we know that first class constraints generate gauge symmetries. So the total number of degrees of freedom for lambda and W will be 16 plus 16 minus 7 from the constraints and minus 7 from the gauge symmetry. So I will have 18. And here I will have 10 minus 1 from this constraint and minus 1 from the gauge symmetry generated by this constraint. So I will have 8. So the counting is correct. Okay. Nice. So, okay, so I have this model, these equations. Okay, and now, I can use these equations in order to rewrite this action in terms of the supertwistor variables. When I do that, I get that the action in the twistor description is just given by something like this: W alpha, lambda dot alpha, plus psi dot m, plus G alpha plus, sorry, let me put here H alpha, and here GTF. This is a Lagrange multiplier, and this is also a Lagrange multiplier. Okay, G alpha is given here, and TF is given here. Okay. Now I will quantize this model in order to figure out how the Bloom and the Bloom polarizations come up in this model. Okay.
So G and T are the only first class, the first class parts?
First class constraints, that's right.
But then there's this is really elementary. Then there's just going to be then a gauge symmetry between H alpha and G because of that constraint. that you mentioned.
That's right, yeah. Yeah, actually you can compute the gauge symmetry just by taking the Poisson bracket of G alpha with W, G alpha with lambda, and so on. Okay, okay, so now let me quantize this. Quantization of the supertwistor model for the superparticle. Okay, in order to do that, I will write the standard commutation relation for lambda and W, and also for psi m and psi, and for the system side. So psi m, psi m, okay. So in order to realize this algebra, I have to represent this psi m as gamma matrices of SO1, 9, right? So psi m will be represented as SO1, 9 gamma matrix, which means 32 times 32 matrices, gamma matrices. Okay, and the wave function will be written as a spin-off representation of SO1, 9, right? So the wave function, which I will denote by phi a, will be SO1, 9 spin-off. Okay. Okay. So now
that's a full Dirac spinner of SO1.
Yeah, that's right. So it's a 32 components. Okay, so now I can write DG alpha and TF in the lambda representation, for example. And when I do that, let me write here. No, maybe here. So I will have something like this: G alpha and B acting on the wave function phi b, which is equal to lambda gamma and lambda. Gamma m partial with respect to lambda alpha minus 2 lambda alpha, lambda partial with respect to lambda phi a, right? And for the psi variables, I will have gamma m, lambda alpha, gamma m, a and b, phi b. Okay. And the same thing for TF. So for TF, I will have something like this: lambda, gamma, and lambda, gamma, and AB, phi B. Right? So right here, B, phi B. Okay.
Sorry, could you repeat what phi is? Why does it depend on lambda?
Sorry?
Phi depends on lambda?
Yeah, right. Because I mean, you can choose a representation, right? I'm working now on the lambda representation where phi is only a function of lambda and psi.
So in other words, like lambda is like x and W is like p in a standard quantum calculation.
Yeah.
And then I value, because I've got the psi Clifford algebra, I'm just valuing this in SO1.
That's right. That's right.
Phi is the new wave function.
Phi is the wave function, that's right. Okay, so let me say a comment here. Turns out that in order for this condition to be satisfied, I have to add here a new term, which can be explained from normal ordering ambiguities. So the term is something like this, lambda alpha phi here. So if you add this, you can see that at a quantum level, this condition is respected. Okay. In order to solve this,
So can I just ask, so is there an easy way to see why, sort of like elementary, why is that term not there classically?
Why is not classically? Because you have to take into account the normal ordering coming from, for example, this kind of terms. Because lambda W has a no vanishing relation commutation, right? So you have to regularize this.
You think where to put the derivatives in the first line, right? All the derivatives are to the right. So
Yeah.
it could have been that the last term on the first
Right.
line?
Yeah.
If you integrate it by parts, you're gonna generate the term you're asking about.
Well, I guess a equivalent way of formulating my statement is, if in G alpha, if I added lambda alpha to that, could I see that that's not doing anything?
Are they should have opposite curve.
Sorry, could you repeat?
Sorry, it was just, I was just trying, so I can sort of look at every term that you have written there and identify, I can see where it's coming from the classical description of G alpha. I'm just wondering, naively, it looks like in a sense, all that I've added is a lambda alpha term over to this G alpha in the classical description.
Yeah,
But I assume that that's not valid classically.
that's right. Yeah, that's not very classical. Yeah. So you have to add it in order to respect that condition, right? I mean, HM. Okay.
We would need to add to G, we need to take G to lambda times the unit operator.
That,
Right? There's DAB.
yeah, okay, so,
okay.
yeah, something like.
Oh, I see.
Delta
Okay,
E
okay. I
by
see.
pi B.
Right.
Okay, so in order to solve this, I mean.
Can I just, because there was a question about it earlier anyway. The gauge symmetry between between the G terms in there in the last line of the pure spinner, of the twistor form, yeah? Is that the remnant of kappa symmetry? Is that what
Yeah, it's
replaces
related to
kappa
the
symmetry?
symmetry, that's right, yeah, that's correct. Okay,
Max, you may not want to use that word, the shop word, because
I don't use this?
well, it gets a little bit, it's hard to.
On the bottom, the screen is in the way, we can't see.
Maybe I can go to the first. Okay, so the first. Okay, so now, in order to solve these two constraints at a quantum level, I have to decompose the SO1 common I spinor phi A into the chiral components. I mean, the violent and anti-violent components. So phi A, I will write this way. Okay. And now it turns out that, for example, phi alpha can be written like this. And phi alpha with the upper index can be written like this. Lambda alpha, lambda b minus, okay, there is a factor here, okay, 1/4, lambda gamma and lambda, gamma and b alpha. So if you put these expressions into the conditions for G and TF, you solve identically these two conditions, these two equations, okay?
Could you explain what you wrote? So lambda looks like capital B, but you mean lowercase b?
This one?
Underneath it.
Sorry, again?
Underneath that, which B is that?
Sorry, yeah, okay. So B is an arbitrary field, okay, so B alpha and again. Turns out that, okay, this is a solution of that,
I see.
as long as AM, lambda gamma, and lambda yeah, this should be 0, okay? And this is arbitrary, okay? Okay.
And what's the last thing you wrote? Gamma?
Lambda, gamma m lambda, gamma m alpha. Gamma m, sorry, gamma m b alpha. Sorry about that. Okay, so, yeah, please.
So you're saying, so B alpha is totally arbitrary, but AM is just subject to that
Yeah.
constraint?
Yeah.
Okay.
Yeah, now I'm gonna, okay. It turns out that these two expressions are invariant under some transformations. So, for example, AM, if I change AM by AM plus lambda gamma and lambda times some gauge parameter f, this expression is invariant, right? By the 10-dimensional Frisk identity.
It's even bigger than that, right?
Sorry?
Even more than that, right? Lambda, gamma, any spinner.
No, because it's not a pure spinner. It's a constrained spinner. So you have to use that gamma n, alpha, beta, gamma n, delta, sigma, the 3 indexes. So you need 3 lambdas.
Oh, I'm sorry, I thought you were saying oh, sorry, it's a symmetry of the constraint, but it's also, okay.
Oh, yeah. Sorry, yeah. Of this, so sorry. Maybe I should. So this is invariant, it's gauge invariant when AM changed by this expression. Okay. And this expression is gauge invariant when the alpha change by this expression. Plus lambda gamma m, lambda gamma m, some, I don't know, f tilde alpha. Okay. So I'm gonna construct a gauge invariant object. I mean, a gauge, an object which is gauge invariant under this gauge transformation, and I will call this object C alpha. This C alpha is given by this expression, gamma n b alpha. Okay. Okay. So by using this definition for C alpha, one can show that lambda gamma n lambda gamma n C alpha is 0, which is the Theodoratic equation for the Guillen. And this is the gluon, right? So the gluon and the gluino here, see, come up in the formalism through these equations. Okay.
The gluon's in Lorentz gauge?
So yeah, that's right. In the Lorentz gauge, because this condition should be satisfied. Yeah. Like in standard string theory, right? When you quantize, you have to impose that Q of B should be 0, and delta of B should be here exact, and you get that Kn, An for the strings, Im, An to the minus pi over 2. See, this An should be satisfied this condition, right? It's the same thing here.
Where's the rest of the Maxwell equation?
But you are in the Lorentz gauge, so the other terms are 0.
Yeah,
right?
where's the box A is 0 term?
But that condition doesn't give you, I mean, doesn't.
Oh, p squared is 0, yeah, sorry.
Okay.
So, I got lost. When did, oh, P squared is 0 because of the identity. Okay.
Yeah, that's right.
Yeah.
Okay, so. Okay, so now I'm going to introduce the.
So just so we can follow. So you're doing a twistor description. So there's the p squared equals 0 is already being solved
That's
in
right.
terms of lambda,
Uh-huh.
and then the Maxwell equation reduces to the Lorentz gauge condition,
Yeah.
and that's what you're recovering there.
That's right.
I see. And then separately the Dirac equation has to work its own.
Huh? Correct. Okay, now I'm going to use this action for the twistor model of the superparticle, and I'm going to introduce the Ambitwistor string using Supertwistors. Okay. So part of the talk is the Supertwistor, Ambitwistor, string action.
I just ask one question. I'm a little bit confused by one thing. So I can see now that the gauge symmetry that you wrote for A is basically just the standard gauge transformation.
Yeah, that's right.
Is there some significance to B alpha?
Sorry.
Now the equation below it, there's some B alpha that has a gauge symmetry from which you construct a field strength with which is C alpha.
Yeah.
And you're interpreting C alpha as the Guillen.
Like the Guillen, that's
What
right.
is the interpretation of B alpha?
I mean, you mean the physical interpretation of the alpha?
Yeah, I mean, does that have some interpretation? Is that like the superspace fermionic connection or something?
Is it the Guillen?
Yeah, it looks like a pre-potential for the Guillen is what I'm trying to say.
Yeah, I think it's like the Guillen, but with a gauge transformation. So if you want to work with something which is invariant, which is gauge invariant, you have to construct this. But it's essentially the Guillen, but you have to add the gauge transformation. So it's like like you say, the pre-potential for the Guillen, right? Like AM, right? For the Guillen, but now for the Guillen could be the alpha. Yeah. But it's common to work with a gauge invariant object, which is the alpha. That's right. Okay. So the action. Okay. So the Ambitwistor string theory was introduced by Mason and Skinner, and it was obtained by changing the time derivatives of the spin and particle by antilomorphic derivatives, and the word line by the CP1 manifold. Okay. So I'm gonna do the same thing here. I'm gonna change time derivatives by antilomorphic derivatives. So let me put here the Riemann surface or the Riemann sphere. One. Okay. I will have here W alpha, V bar lambda alpha plus psi m, V bar psi m plus the constraints, right? Which are H alpha, G alpha plus GTF, and now I will introduce the standard term, which is B bar C, which comes from diffeomorphism, right? But on the worksheet, okay. So plus the action for the current algebra sector, okay, SJ. Okay. So the OB is here.
Sorry, what did you say? I just didn't miss it. What's S sub J?
SJ is the current algebra action, like in EEA, times CA, heterotic string. Yeah, sorry, so this is the heterotic model for the Ambitwistor, Supertwistor, Ambitwistor. Okay. Yeah, actually you can do also type 2B, and you have to introduce a new psi tilde m variable, okay? And it's okay, so let me put here type 2B. So it's given by this action, psi m plus psi tilde m plus H alpha, G alpha plus GTF plus G tilde, TF tilde plus B bar C. Okay, so this is the heterotic model, and this is the type 2B model. In this case, for example, the equation for W alpha changed in this way. You will have gamma m lambda alpha xm plus psi m gamma m theta alpha plus psi tilde m gamma m theta alpha, theta tilde alpha, because it's an n equals to supersymmetry, right? And of course, you will have psi m lambda gamma m theta and psi tilde m lambda gamma m theta tilde. Okay. Okay. So now let me count the central charges for this model, coming from the matter sector and also from the go sector, in order to see what is the space-time. I mean, what is the target, the dimension of the target space, which makes this model critical. Okay. Sorry, this is important. So now we have these goals, right? B alpha, C alpha for G alpha, and also beta and gamma for TF. But we also have now these B and C goals coming from the diffeomorphism symmetry. Okay? So let me count the central charges. So for example, the total central charge for this model comes from matter and goals. Right? So for matter, we have lambda and W and also psi m, right? So this is given by 2 minus 4D. D is the dimension of the target space, right? Plus D over 2, which is the central charge for the system psi. This is the central charge for the system lambda and W, okay? Also, let me see here. Yeah, and we also have this ghost, okay, which is minus 26 plus 11 as in standard string theory. But we also have this goes here and this goes here. So let me put here we will have plus 11 40 minus 2 plus 26 D minus this goes have conformal weight 3 and minus 2. So this has 3, for example, and this has minus 2. So the central charge is 74. And also the central charge coming from the current sector, right? SJ.
Can you repeat how you got the 4D minus 2 combination?
Yeah, okay. It turns out that this Supertwistor description works in equals 3, 4, 6, and 10. Because in these cases, you can use this identity, right?
Yeah.
So, okay. So the dimension of lambda alpha and W alpha in these cases is given by this expression, 2 minus 4D. That's right? Okay. So if you do this algebra problem, you can see that if D is equal to 10, CG should be 16, which is the standard central charge for the EA cross EA model and SO32 heterotic string. Right? Turns out that for this model, you can also do discounting, and you will get that okay, this is heterotic, and for type 2B, you get that if D is equal to 10, C is 0. So D equals 10 is a critical dimension for these string theories. Okay?
Now, just to remind me, I mean, this is an Ambitwistor string, so this is not exact. This isn't identical to the original natural RNS formulation of these things.
No, it's not the Ramon neutral formalism.
Right. So, like, is there some limiting procedure by which I can arrive at the Ambitwistor string?
Yeah, there is. That's a very good question. There is a nice paper in the, I think 2 months ago by Henan Lipinski. It has to do with the gauge choice that one can make. For example, let me remember well. Okay, so it turns out that the Lagrange multiplier for the diffeomorphism symmetry, which I will call E, can be written in this form: 1 plus beta over 1 minus beta. Okay, so 1 beta.
Beta is the beta comes.
No, it's just a parameter. Let me put beta tilde. Okay. Okay, so like maybe here. I think it's minus. So if beta tilde is equal to 1, you get the conformal gauge of a string theory. Okay. If beta tilde is equal to 0, you get the Lycon gauge. If beta tilde is equal to infinity, you get Ambitwistor string. That's how this Ambitwistor string arises from this string theory. It's just like a singular gauge choice of the diffeomorphism Lagrange multiplier. Okay.
But then it's equivalent, right? I mean, if it's just a gauge choice, right? Then physically the spectra are going to be You actually do the spectral analysis.
Yeah, but it's a singular gauge choice. It's not a standard gauge choice.
Okay.
That's
It's not
why
really
the
valid.
spectrum is not the same.
So again,
It's not really a valid gauge choice.
okay.
You can get there by doing it, but you're not honestly allowed to gauge fix to that.
Yeah.
It takes a singular gauge transformation to get there, which
Right,
you're not
okay.
allowed to do.
Yeah.
Because originally E is assumed to be some positive number, so how are you gonna?
Yeah.
So
So yeah, actually,
I'm not matching to his actual limits. I don't know whether that's the right thing to do, but there is, the one that you're talking about is the singular one.
Okay.
So yeah, actually here the spectrum that you get here is just massless modes. You don't get bandless modes. You don't get the infinite power of massive modes of string theory for the Ambitwistor string. Okay, that's that different compared to ordinary string theory. However, this is a nice formalism to describe the CHY formula for the interaction of massless particles in any space-time dimension of quantum field theories. Okay. Okay, so I have 15 minutes. So okay. Yeah. So the idea here could be try to construct the VRC operator and then construct the VRC closest vertex operator in order to compute the scattering amplitude, so endpoint correlation function, right? The problem is that it's very complicated because we will have goes for goes and goes for goes for goes and so on here. Okay. So there is a nice way to figure out how to compute the scattering amplitudes, and this formalism has to do with the Lycon gauge analysis of this model. In order to do that, I will fix all of the gauge symmetries, which means fixing G alpha, TF, and also the symmetry coming from the diffeomorphism. So here, so let me write here more or less the action. Plus H alpha, G alpha, plus G, and also I will have here E tilde, W alpha, partial lambda alpha, minus partial W alpha, lambda alpha, plus n, which is the stress energy tensor of the model, right? And also I have plus this. Okay. This part is a little heavy, so.
So just make sure you're starting from the heterotic action and you're coming over.
Yeah, this is the adaptive action, but I didn't fix the diffeomorphism symmetry, so I don't have to write this term. I just have to write the Lagrange multiplier times the stress energy tensor, which is the expression. Okay, so now I will use, for example, the G alpha symmetry in order to fix 7 components of lambda alpha. So in order to do that, I will write lambda alpha in terms of the SOA components, lambda A, lambda dot, okay? And if I use this gauge symmetry, I can fix, for example, lambda A to this form, lambda plus, with 7 zeros. Okay? And the same thing I can do with W alpha if I try to solve G alpha. So W alpha can write like W plus, 7 zeros here, and W A dot. Okay, where A and A dot comes from course 1 to 8. Okay, now I can use, for example, TF in order to fix psi minus. Okay, so for example, if I use TF, I can fix plus equals to 0, and also psi minus equals to pi psi I over p plus, right? So, and now I can use the gauge symmetry coming from this p tilde in order to fix lambda plus in the Lycon coordinate, which is given by this coordinate, r plus sigma, okay, equals to 1.
The one above it, you just said, the psi plus, you're fixing using TF? What did you just say?
This
Yeah.
is
TF, okay.
by TF, and this
That's
is by
detailed.
by TB. This is TB, which is the stress energy tension. Okay, so if I use TF, I can fix this, and if I use TB, I can fix this, and I can solve this constraint in order to write the partial of W plus equals to okay, psi m, partial psi m over lambda plus. Okay. No, sorry. No, yeah, that's fine.
And why is there a subscript
Yes.
on lambda plus?
Sorry?
I didn't understand why there's a row on lambda plus.
This one?
Yeah?
What is the row? You mean?
There's a subscript, it looks like a row.
Row is the Lycon coordinate, which is like
Why does lambda have one?
it's like in standard string theory, you fix p plus equals to 1, right?
Yeah, but that's a one form before you do that, right?
Yeah, but p plus is lambda squared. It's lambda times squared.
Okay.
Yeah. Okay. Yeah. Yeah, actually, it
Lambda
would be-
carries a certain conformal weight or something, and this is being tracked by the row.
by the row. That's right. Yeah. Okay. I just have 10 minutes, so.
Max, if you write any lower, then people, the view will be obstructed by the screen.
Yeah. Sorry. Oh, thank you about that. Yeah. Okay. Sorry. Okay, so now my action, my final action, or the resulting action after fixing those symmetries would be, would like this. In the Lycon gauge, the Supertwistor and Ambitwistor string is given by W alpha, lambda bar lambda alpha, plus psi n, lambda bar psi n, and that's all. Oh, sorry, here is a dot, psi I, where I is an SOA vector index, and this is like an anti-bar SOA vector. SOA spinor, sorry. Okay. And this is in the Riemann surface. Okay. Okay, now I can try to construct the vertex operators in the Lycon gauge. Okay. In order to do that, I have to introduce the momentum eigenvector, right? Like in a standard string theory, we know that E k dot x is the eigenvector, is the momentum eigenvector for the states, for the physical states, right? So in this case, we will have that e to the k dot w dot over 2 lambda plus satisfies, plays the same role of this e to the I k dot x. And we can see that by using the standard incidence relation that I wrote before there. I mean, the relation between W alpha and Xn and psi A and so on. Okay? Okay. Now, I can write the vertex operators for the blue and for the Guillen, right? In order to do that, I have to bosonize this II, because in this model, the physical states would be placed in the Ramon sector, and we can see that from the supersymmetry generator, for example. Let me explain that.
What's in the connection? To the nabla bar, what is that covariantization?
Ah, yeah, sorry. Nabla bar means that nabla bar acting on lambda plus is 0 in any coordinate system. Yeah, so now, for example, if you introduce this, like the exponential of the vertex operators, you can compute the equation of motion for lambda I dot, for example, and you will see that that's given, that's solved when lambda I dot takes this form. Okay, which is equivalent to pi KIR minus ER, which is the expression which is the transverse coordinate of Pn, but it's the same expression that you get in the standard Ambitwistor string, which is given by Pm, KMR, over C minus CR. This is the covariant way of writing Pn in terms of K. This is the transverse notation, and this is equivalent to this, which is the twistor version of this. Okay.
Sorry, where did you get that equation?
Which equation? This one?
You said something about lambda equation of motion, and then it looks like you wrote down the answer.
Yeah, you have to introduce the vertex operators. You have here R, right, and from 1 to n. Now you have to deduce the equation of motion for W dot, and you will get the equation of motion for nabla bar lambda dot. In order to solve that, you will have nabla bar lambda dot, sum of deltas C minus R, KR, dot over lambda plus, right? So it turns out that this equation, this expression, when you put this equation here, you solve this equation. Okay, so, and this expression is equivalent to this, which is equivalent to the standard Ambitwistor. So this is a twistor version of the Pn in the Ambitwistor. Nice. Now let me write the vertex operators. I just have 5 minutes, so I'm going to finish this here. Okay, so the vertex operator for the gluon, okay, could be equal to sigma I plus A dot. This plus is the same component of the plus that I fixed here by using G alpha, which is like the first component of the lambda A spin or Weil spin of the SOA, okay? And here I will have sigma I dot, where this sigma I dot is obtained by bosonizing this psi I, okay? So, for example, if I write psi 2j plus minus I psi 2j minus 1, like, sorry, minus 1 here, equals to e to the IH, ij, for example, plus minus, no, yeah, it's fine. Yeah, plus minus here. We can write, for example, sigma I dot, or sigma A, like e to the sum from 1 to 4 plus minus a half hk. Okay, and sigma A dot. This is when you have even minus. Okay, and this is when you have odd minus. Into the same expression here. So this is the bosonization of the size. Okay. Okay, so if I use this sigma A dot, for example, here, I can write the vertex operator for the gluon in this model. So I will have here AI and the exponential that I wrote here. Okay. So the same exponential that I wrote there. Okay. And for the gluino, we can write something like this. Remember, well, it's like CA dot, sigma A dot, plus delta, sorry, sigma A, delta A plus, sigma plus, okay, and the exponential, okay? But also in the Lycon gauge, like in standard string theory, we have to introduce the interaction point operators, right? Because in this map, when we analyze this map, the Mandelstam map, which is given by, if you solve this, you will have that rho should be given by this expression. K plus log of C minus CR, where this C is the coordinate in the C plane. Okay? So when you analyze this, you will see that there will be some points, okay, in the C coordinate, which makes the first derivative of rho equals to 0. Okay, these points are called interaction points. Okay, And these points are important in order to define this prescription for the prescription for the scattering amplitudes in this model. Okay. So let me write here just to finish the interaction point vertex. Okay. This is given by lambda a dot, sigma a dot, delta of lambda a dot, lambda a dot, and here you will have partial rho with respect to C and 1 over 4. You have to add this term in order to have a conformal weight 0 vertex here. Okay. Okay, so the prescription is that you have to introduce n vertices for the external states. I mean, for n-point interactions, you have to introduce n vertices. So you will have B1, C1, B2, C2, until Bn, Cn, and you have to introduce n minus 2 interaction point vertices. Okay. So interaction point C1 until interaction point is C tilde 1, C tilde n minus 2. Okay. In this case, these C's, these CRs satisfies these scattering equations, and this C tilde alpha satisfies the constraint that the first derivative of rho should be 0. Okay. So turns out that it's possible to show that this prescription coincides to the standard prescription in the Ramon-Nibiu-Schwarz Ambitwistor string, which describes correctly the CHY formula for the interaction of massless particles of quantum field theories, like, for example, supergravity and superdynamics, right? And also this, it's not conformal supergravity, but it's similar to a conformal supergravity in 10 dimensions. So yeah, I think it's 3 p.m.